Hello, this is Bruce Wallenberg. This is the lecture number 6 in our series on power generation, operation, and control. This is a lecture again dealing with optimization theory, and this particular lecture is on dynamic programming. We're going to start with a sample here. We're going to assume that we have a city, we'll call it A, and we want to get across the country to N. So assume that these are all cities. The circles represent cities, and we're going to do is we're going to say that we blocked it off into 5 steps here, 5 zones, whatever you want to call it. And in each zone, we have a set of cities. In this case, we have 3 here, 4 at this boundary, and 2 at this boundary. And the idea is to find the optimal path where the number here, if you notice, we have a number right here, is the cost to travel from A to B. If I went from A to C, however, it would be a cost of only 2. If I went from A to D, it's a cost of 3. So the idea here is that we'd like to get from A to N at the minimum cost. We want to get to A to N at the minimum cost. And this process of dynamic programming can solve that problem in a very, very nice way. The principle of optimality says that an optimal policy must contain only optimal sub-policies. Well, we'll show you what that really means in our context here. But it's a better thing to say an optimal policy is optimal if at a stage. Now that's those vertical lines, those zonal lines that I showed you. If at a stage, whatever the preceding decisions may have been, the decisions still to be taken constitute an optimal policy when the result of the previous decisions is included. Just bear with us here, and we'll explain that in a little bit more detail. But we'll say that we'll show you this in this particular diagram here. I'm going to use a notation here where I'm going to move the city, the letter. So if you know, this is B here, and this is 5, and this is H and 13. Well, this number in the lower half of the circle is the minimum cost to reach that city. So if I go from A to B, there is only one path, and so the cost is 5. So you see the 5 right in here. A to C, the cost is 2 because that's the only path there, and A to D is the cost is 3. Now we begin to have some decisions to make. So if I look at the city E, if I go from B to E, okay, the cost to get to B was 5, and then the cost from there to E was 11, and so that would be a cost of 16. If I went through C, from A to C, the cost was 2, and then I went up this way, the cost was 10. So we would say this represents the optimal path to get to E. Okay, I haven't yet said anything about whether this is the final optimal path to get all the way to N, but this is the path. So I'm going to put a little asterisk here, meaning that's the path, that's the best path to get to city E, because it's cheaper. It's 10 versus 16, and we want the cheapest path. So I now know the cheapest path to get to 10, and if I then follow any other set of paths to get to N, I know that once I get to E, the best path is going back this way to C and then to A. So we're going to say that we're going to solve this, and we're solving it in the forward direction, where forward looks this way from the end. You can also solve it by starting at N and working your way back. The same logic, although you have to apply it differently because you're going in the opposite direction. So that this would be forward F, this would be backward B. Now, for most of the problems that we're going to solve in this text, we're going to stick with the forward method. It makes the most sense, and especially when this is not distance along across a country, it could be time steps. Well, usually we say time goes in the forward direction. Okay, now F, it could be 2 plus 4, or it could be 3 down here. I could come from D to F, which is 3 plus 6 is 9. So 2 plus 4, this one I should have put 6. So the optimum path, if I were suddenly found myself at F, would be this one. I would go back this way. Let me put I would go back from F to C to A. If I got to E, the asterisk says you go from E to C to A. Okay, now if I want to look at G down here, I could come all the way down from C. That's 2 plus 9 is 11. Or I can come from D, which is 3 plus 6, which is 9. Well, if that's the case, the red markings are the travel to the block, or to the city, pardon me. So 9 is the optimal. It's the least cost. Remember, we said this is 2 plus 9 or 11. So this path down here back to D is the optimal path. So now I'm done with this stage, and this is where the principle of optimality comes in, and it says, okay, I know the optimal path to each of those cities. When I go to the next stage over here, to this boundary between region 3 and 4, all I have to do is find the best path back to one of the cities at this 2-3 boundary. And if I know the best path there, then I know the best path from here back to here and here back to A. Okay, so let's start with the top here at 13. Pardon me, the minimum is 13. Well, if this is 10 and I go up this path, it's 10 plus 3 is 13. So once again, it's the 10 here, the optimal cost at E, the minimum cost to get to E, plus 3 is 13. There's the 13 in there. Now if I go to I, it could be 10 plus 2 if I followed this one, which would be 12. Or it could be 6 plus 11, or 17. And so it's the minimum cost is going back by this path here. And we should have marked this one here. By the way, let me finish this one. H, I'm getting to H. This is 13 up this way. If I came from F, it would be 6 and 8. It would be 14. So it would be 14. So this is the optimum path. So once again, I now know that if I got to H, then the asterisk says the cheapest path away from H going back to the start is this path. And if I get to E, the cheapest path is this path. Here there's only one path. So now I know the cheapest path is 13 to get all the way from A up to H. Here we had 12 or 17, so we know the optimal cost is 12. Here there's only one path into J, so, and that's this path here, and that would be a cost of 11. and so the optimum path is here. It's actually the only path, so we'll mark it that way. Here I could come down 6 and 9, and that would be 15, whereas 9 and 4 would be 13. So again, we know the optimum path is this one down here. Okay, so at the 3-4 boundary, at the third stage, if you will, I have the optimum path to get to each one of these cities. And the idea is now I'm going to go to the next stage, and I don't care what I did back here to get to these cities. All I need to know is what that number is. How much did it cost me to get there? How much does it cost to get to the next stage? So here is 13 and 9, or 12 and 3. Well, this is 22. This is a very large cost to come down there, whereas this is 12 and 3, or 15. So there's the optimum path from L. From M, oh, pardon me, we actually have a third path coming in here. 11 and 7 is 18. So we did choose the optimum path. It's this one here with the asterisk. 6 to get from I to M. So to come down this path, it's 6, and 12 is 18. To come here, it's 11, and 18 is 19. And to come here, it's 13, and 5 is only 18. Now here we have an interesting thing, and that is that at M I have the same cost if I came down this one. I'm going to put the asterisk there, as it was here, and it turns out that either one of these will end up with the same overall cost. And now last of all, I go to the final, and once again, it doesn't matter when I evaluate these how I got to L or M. It's the cost. It's 15. 15 encapsulates the entire cost on the minimum path to L. 18 captures or encapsulates the minimum cost, whether it's this path back to here, back to I, E, C, A, or K, G, and let's see, and then back to D, and then back. Okay, at N, it's 15 plus 4, 19, or 18 plus 3 is 21. So here's our optimum path right here. Now, if that's the case, we know the overall optimum path. Let's see if I can do this. We'll sort of color it in. So that goes back here, and then it comes back here. So we went from N to L to I to E, back to 8, back to C, pardon me, and back to 2. So once again, the minimum cost to N was 19, and that meant we follow the asterisk. Well, if this is the asterisk is here, so we go back to L. Now you look for the asterisk and you follow it, and so this is the path, and it costs us 19. It would have cost 21 if we'd have come down through here. Now there are paths that could be very, very expensive. If I decided, for example, to go up here, and then I went all the way down here and down and back, that would not be necessarily an optimal path, and I could even make the cost higher. But this is the minimum cost. We are seeking the minimum cost. So I find, and this process will work for any number of stages. Any number of stages. Mathematically, we say if x of I are the choices at the end of each stage. For example, at stage 3, the choices are H, I, J, and K. So that's where we get this here. That's the stages here at the end of stage 3. inside that circle. Then v of a from I to I plus 1, this cost is the cost to travel from city I to city I plus 1, and f is a minimum cost to arrive at city I at the end of a stage starting from A. Well, this is the number that you see if I drew the circle and I put the whatever was up here, and for example, I had an n here. Well, this is the cost. Okay, that's this number that I put up here as the minimum cost. And that's the mathematical statement of the problem. Now, the mathematics of dynamic programming. We said the set of places, the cities are x0 is A. Then the next set is E, F, G, L, M, B, C, D, H, I, J, K, and N. Okay, actually these go 0, 1, 2, 3, 4, 5. So in order they go like this. The minimum cost for the first stage is obvious, and we did that one. Okay, because there's only one path. The minimum cost for stages 1 and 2 is a function of x2, and these are the same. This says that for example, at x1, if I'm going to E, it's 5 plus 11, 2 plus 8, or 3 plus. That's interesting. Let's. I'm sorry. We're looking at this right here, and we're saying as a stages 1 and 2 as a function of x2, we're going to minimize the cost plus this you say is the minimum to get to that point, and then this is to traverse the thing. And all we are meaning here is that 5 plus 11, 2 plus 8, 5. Here's the 5 plus 11. I'll put the pointer on here. 5 plus 11, 2 plus 8. Or let's see here, we said it could be 3 plus infinity, and actually that's a that's a typo. That should be the 9, but in any event, so this would be x1 is B, C, D, and x1 is equal to C. And so you can see that these mathematically, we go through these steps, and at N we reach the conclusion that the minimum cost is 9, and that we have left pointers along the way that say, well, how do you get back? What's the pointer back to the previous stage? Now, this is a different kind of problem that uses dynamic programming. It's called an allocation problem. The idea is that I have, let's say, 4 businesses or 4 divisions of my company. And I would like to allocate a certain amount of resources, which are x1, 2, 3, and 4. And I would like to allocate resources, and if I allocate an amount x1, then I make a profit of v of x1. V of x2, V of x3, V of x4, and I add them together to get the total over here. Well, how do I allocate? Let's say I have a certain total that I can put in here. How do I break it up? How do I break it up to get this maximum? And it gets to be a very large. If you just simply said, well, we'll just do all the permutations and combinations or whatever of ways of allocating, you'll be there for hours and hours trying to solve it. So the first thing I'm going to do is just simply say, well, what is the stage 1 problem? And the idea here is to say, okay, look, I start out and I'm given U1, which is simply the total that I can allocate between x1 and x2. And again, if I allocate x1, I get v of x1 and v of x2. Now, the maximum over here, the maximum over here, is the maximum of V1 of X1, and if I allocate X1 to V1, well then the other one is X2 is equal to U1 minus X1. Okay, so this says whatever I take of U1 and I put X1 into division 1 of my company, then the remainder is U1 minus X2, minus X1, that goes into V2, and all I have to do is say, well, I'm gonna determine what this number would be for different values of U1. This is the secret of it, is to say, look, we've broken it into to just 2 allocations here, and I'm going to step through a set of values of U1. So let's start out here. The values of X1 to U1 could be anywhere from 0 to 10 integers. Okay, if I allocate 0 to these, we're given the fact that V1 of 0 is 0, so is V2 of 0. If I give you 0 to invest in those divisions of my company, I'm going to get 0 back. Now, if I said I'm going to allocate one object, then V1 of X would be 2.8, and V2 would be 0, or I allocated 0 to V1 and then the 1 to V2, and I only got 2.5. Therefore, the optimum for this value of U1 equals 1 is 2.8. It's this one. We take the maximum. So the optimal sub-policy is to allocate 1 to X1 and 0 to X2. 1 to X1, 0 to X2. Now I do it for 2. Now 2, if I have 2 objects, you could say $2, or it could be $2 million, so it doesn't matter. We just have the unit 2. If I can invest 2 here, I would allocate, if I could do 2 into V1 and get 45, or 2 into V2 and get 41, or I could do 1 each. Now I can go back here and I can sum over these, which you notice is what is greater than either of these. It's 53.53. So here's the optimum, and we say that it's here. It's 1 and 1. Okay, 3. If I'm allocating 3, I can put 3 here is 65, or 3 here is 55. Well, how can I get 70? Okay, how can I get 70? Well, the answer is you would put 2 here and 1 here, okay, and that is going to give you 70. So here's the optimal allocation, 2 plus 1. And we keep going like this all the way up to 10. This is the value of U, and the whole idea is to look at the end and say, look, I have a table for F2 of U1, and this is the value of U1, and that's all I need to retain. I don't have to know anything more about V1 and V2 and X1 and X2. I have developed the optimal, and these are the allocations of those X1 and X2. Okay, now I simply say, okay, here is U1 and stage 2 to get F2 of U1. Now let's come back here. I need this table. So that table that I just developed is used for this one. This one I have to have the X3 V of X3 table up here. It should be V3 of X3. If we could add a subscript to it down there. So now I say, okay, I've got U2 to invest, and if I put U1 into here, I get this much. Then X3 is what? That's U2 minus U1. So that's this amount over here in the X3. That's X3. So we now have a table that looks like this, and you'll notice now that you don't see X1 or X2 anymore. You see this that we generated before, and we have a table for X3 for 1, 2, 3, 4, 5, all the way up to 10. And we just start and we say, okay, if I'm going to allocate 0, once again I get 0. If I'm going to allocate 1, I will either allocate it and use this or this. Well, it's this one here. Now that one, it turns out, is for 1 and 2 was this policy. Now I'm on this column right here. I'm adding this to it. So the optimal allocation of 1 is to put it into division 1 or business number 1 and forget the other 2. And then I allocate 2. And I get the optimal over here, and it says that is to simply that the 2 would have been the original. Remember, this is the original out here of the first 2 objects, to use just 1 and 1 and not allocate to anything. And it turns out that it's best up to this point to just use the first 2 businesses. Now here it turns out that we're a little better off to start to spread the allocation around, and instead of going 3, 3, we go 3, 2, 1, 3, 3, 1, and so forth. Here we have a split. It can be either way, and you get the same cost. So now we have created the table for F3 of U2, and there's the U1 or U2 or X. And now we're going to use this table, and that table of F3 of U2 is put into this stage 3, and we've now got the 4th business or the 4th division of our company, and here's our total investment A. And it simply says we're maximizing F3 of U2. Now that's F3 of U2 is this table plus V4 of A minus A minus U2. So if U2 comes up here, then this amount down here, X4, is A minus U2. And we do this once again. Now here's the table we developed last time. Here's the X4 allocation, the profits from X4, and this is the table F4. This is the final table over here, and this gives you the optimal allocation. A couple places there were allocations that gave us the same result. But then the other thing we want to do is, well, now what over all of this, over all of these, I want to know the max, right? I want to maximize the profits. So here the max, and that's this number, 1.81. So there is the final answer. If you're allocating 10 objects, $10 million to your business, you would allocate it 4 to the first venture or first division or business, 3 to the next, 1 to the next, and 2 to the next. So we have solved this this allocation problem. Now we're going to use this later on to show a very interesting way to do economic generation dispatch. So we thank you very much, and we hope that this has been helpful, and this will be a good lead-in for the chapters on unit commitment, where we use dynamic programming.